Taphole length is measured from the inner hot face to the outer shell, as it is very common to each operators. So from inner face to of the refractory to the outer shell is a basically critical design variable. So why critical? Because if the taphole is too short, the iron will erode the clay quickly and you risk a breakout. So molten metal bursting out uncontrollably also. So if it is too long, the drill cannot reach the end properly and you waste time and clay. So designing the correct taphole length gives you safe, a stable flow and a predictable tapping operation. So that's what this session is all about. So coming to the blast furnace tapping slide, as it shows that now let's look at the parameters that control taphole design. First, daily production. Here we take 7,500 ton per day as an example. Second, productivity in tonnage per cubic meter per day, typically between 2.2 to 2.8. Higher productivity often means a higher tapping frequency because you push the furnace harder. And third, the tapping time per cast. For large blast furnaces, this is usually 60 to 90 minutes. From these, we calculate the tapping rate in tons per minute. The formula is tapping rate tons per minute is equal to TPD divided by total tapping minutes per day. So total tapping minutes is equal to number of cast per day. So again, I'm repeating that total tapping minutes is equal to number of cast per day into tapping time per cast. So looking at the example at the bottom of the slide, where you can see that 8,000 TPD, 6 cast per day, 80 minute per cast. So total minute is equal to 16 to 80 for 80 minutes. So tapping rate is equal to 8,000 divided by 480, which is 16.7 tons per minute. So this tapping rate is the single most important number for designing taphole length. So remember it. So while designing from next onward, try to remember all these indexes aid in memory so that you can well design this taphole. So coming to our next slide, which is about the blast furnace taphole length calculation steps. So this slide is meant to show the steps by steps calculation, but but it has the numerical examples also attached for your better understanding. So let me walk you through the correct logic that we use in practice. So step one is the determination of tapping rate from the previous slide. We already have a 16.7 ton per minute for the 8,000 TPD. As far as step 2 is concerned, as you can see, uh, that choose a taphole dia. So typically ranges 50 to 70 mm. So larger dia reduces the iron velocity but requires more clay. So for 16.7 ton per minute, we often start with a 60 mm. Step 3, as far as step 3 is concerned, use the empirical rule to estimate the length. One reliable formula from the industry is L in meters is equal to 0.18 into tapping rate plus zero point 0.8 for 16.7 ton per minute. L is equal to 0.18 into 16.7 plus zero point 0.8 is equal to 3.0 plus zero point 0.8, 3.8 meter. That is a big long. So more common is a table at 15 ton per minute, 2.8 meter, at 18 ton per minute, 3.2 meter. So for 16.7 ton per minute, we would design around 3 meters. So as for the step 4 is concerned, adjust for the clay quality and refractory wear. If you have a good high strength clay, you can reduce clay by 5 to 10%. Step 5, always add your safety margin, typically 5% uh, for the new furnace. The key takeaway is the length increases with the tapping rate. So do not guess, calculate using proven correlation. So coming to our after sharing all these slides which are mathematically well calculated and shown to operators for better understanding. coming to this slide, which is about a blast furnace high versus low productivity taphole comparison. So this can, with the help of these numericals, we can able to understand the things much better. So this is a very practical comparison slide. As you can see, on the left, furnace A, uh, we have a furnace A, and which is having a high productivity at 2.7, and uh, yes, this slide actually I was delayed. So TPD is 8,000, but because the productivity is high, the furnace runs with a fewer cast or higher tapping rate. So here 18 ton per minute, taphole dia is 65 mm, and the calculated length is 3.4 meter. So pros is basically less breakout risk, very stable flow. Cons is harder to drill, uses more clay per cast. So on the right, furnace B, lower productivity at 2.0, same 8,000, but because productivity is lower, the tapping rate is only 12. So dia is 60, length is 2.5. Pros is easier drilling, less clay consumption, and cons is higher erosion rate and a shorter campaign before relining. So the important message is higher productivity at same TPD increases the tapping rate, which forces you to use a longer taphole to keep the iron velocity within the safe limit. So when you increase productivity, you must revisit your taphole design. So coming to our very valuable introspection about our learning, whether our taphole length is right or not. So five final check speaking scripts are five checks are there, which we can speak out all the time to on the shop floor while discussing with the operators and all. So final slide is here before you. So use these five checks. Check one is L by D ratio, that is length divided by the diameter, should be between 40 and 60. So below 30, you are at high breakout risk. Above 70, mud injection becomes difficult. For a 3 meter length and 60 meter dia, L by D is equal to 50, perfect. Check 2. Tapping time consistency. If tapping time increases more than 20% over a campaign, your refractory is wearing too fast. That means your length was insufficient. Redesign or change clay. Check 3 is the breakout history. If your furnace has even a taphole breakout or a side out, increase your design length by 10 to 15% next time. So check 4, match with the clay gun capacity. A typically clay gun can inject a clay column of 2.5 to 4 meters. So your designed length must be within that range. Check 5 is productivity adjustment. If you plan to raise productivity above 2.5, you must recheck taphole length. Every 6 months, the adjustment formula given L new is equal to L old, that is length old, into tapping rate new divided by tapping rate old to the power 0.5. So finally, always monitor taphole area temperature with the thermal cameras. Uneven temperature means poor length or bad clay quality.